Today's topic is about chapter 7 and probably like one topic from chapter 8. So today's concept is about like momentum and collision. Probably something that you might have heard the word before, like momentum on a daily basis. You use it for different kind of conversations, like for instance in a soccer game, or this team has a momentum, or in a football game you may hear like, oh, this is the momentum. And then even like for instance maybe in elections you may hear that like, okay, oh, this candidate has the momentum now, and so on and so forth. But in physics, the term momentum may have a different kind of definition. Last week we mentioned something like an object, by virtue of having speed and mass, it has a kinetic energy. And that kinetic energy was calculated as half mv squared, right? And then in today's section, like there's another concept, we call it momentum, somehow related to mass and velocity. In addition to momentum, we are going to talk about like other items such as impulse, right? Probably like you didn't know what impulse is before or something. Maybe you did not hear that word before, but in physics, the term impulse has its own meaning. So we're going to talk about momentum first, and then impulse, and so on and so forth. So okay, all right. So we said first momentum, then impulse, and there will be a little bit of like recoil. We'll talk about like conservation of momentum, and then the different kinds of collisions, and probably at last we're going to touch torque. Okay. So what is momentum? How do we define it in physics? So the linear momentum, of course, we are going to focus on the linear momentum. We're not going to talk about angular momentum. For an object that is rotating, it has also a momentum called angular momentum. But the linear momentum of an object is defined as its mass multiplied by velocity. As you can see here, this equation is the mathematical representation of what momentum is, okay? So every time when you see this little arrow, it doesn't mean much, just tells you that like momentum is a vector quantity, okay? So the little arrow indicates like it's a vector quantity, and then we will be using the direction of the velocity as well. So since velocity is a vector quantity multiplied by a random scalar quantity, which is mass, then in that particular case, what happens is like then the output is going to be a vector quantity, and it acquires the direction of the velocity, literally, okay? So the direction of momentum is the same as the velocities as I just mentioned it, okay? So that's what momentum is. Momentum means like if a car is moving with a certain velocity, then it has momentum. A bowling ball with a velocity has momentum. A golf ball has momentum, and so on and so forth, okay? So then what is impulse then? So impulse is like something related to momentum, but we can also try to explain it in terms of Newton's second law, right? So if you remember, what we know about Newton's second law is the following, right? So what we said about Newton's second law was acceleration, which is a vector quantity, is directly proportional to the force, which is a vector quantity, and inversely proportional to the mass. Okay. So, but from kinematics, if you remember, from kinematics, of course, that force is net force. And from kinematics, we know that the acceleration of an object is its final velocity minus the initial velocity divided by time. So what's going to happen is the following. So from here, from Newton's second law, right, net force is equivalent to mass times acceleration. And then you keep that net force and the mass remains the same. Then from our kinematics, that's chapter 2 and 3, we can take this acceleration and then put it in here. Then what would happen? What's going to happen is the following. You will have V final minus V initial divided by time. Okay. Now, if you take that mass and then multiply everything that is in parentheses, okay, because mass is a common multiplier for V final and V initial, then divided by time. But we already defined that, but we know that momentum, which is represented by uppercase P, is equivalent to mv, right? So therefore, this net force would be equal to P final minus P initial divided by T. How did I get P final? P final is this, mass times final velocity of the object, mass times initial velocity of the object will represent the momentum initial. Now, what you're having here is another definition of Newton's second law. According to Newton's second law, net force is equal to mass times acceleration. But you can also define Newton's second law in terms of momentum. Okay? Newton's second law can be defined as net force is the rate of change in momentum. Okay, then that change in momentum, the change in momentum means the final velocity, the final momentum of an object minus the initial momentum of the object, is defined as impulse. Okay, so that means this F net can be redefined as F net is the rate of change in momentum or the rate of just simply impulse. Therefore, we come up with a new term known as impulse is the same as change in momentum. That's a new definition. Okay, then impulse, which is also a vector quantity, can represent it as like this if you want to, but if we focus on the magnitude, you don't have to put on the arrow, is equal to final momentum minus the initial momentum. So by definition, impulse and change in momentum are the same thing. Okay, now how do you represent this? Like, what is it like? F net is equivalent to Pf minus Pi over T. How do you try to express this in terms of physics, or So what we can see here is the following. So in this equation, you may feel it like if the change in momentum of a certain object. Okay, I'm talking about this equation. If the change in momentum of an equation or an object happens in a long time, then the amount of force experienced by the object can be smaller. Why? Because if you increase the time to change the momentum, right? Because this is like over time, then as time increases, the net force decreases. As time decreases, while the momentum is the same, net force increases. I'm going to give you an example, probably simple one, but pretty much, so let's take an egg. Okay, so we have one egg here. Okay, we have another one here. You're going to drop both of them in the same height. Okay, then here it's a bare floor. Here you're going to put in a pillow. Okay, now you drop the two eggs. The first egg, when you drop it, right, and then the floor will bring it to rest in a very short period of time. Short time. That means high force. Because it's going to have a certain velocity. When it hits the floor, it stops. Then change in momentum happens in a very short period of time. Whereas when you drop something on a pillow, what would happen is like the pillow will act as a cushion, and the contact between the pillow and the egg increases. It will be prolonged. So the exact purpose of the pillow is like to prolong the contact between the egg and the pillow itself, right? So it acts as a cushion, and then like there will be like a slow kind of movement. Like if we try to sit in a microscopic level, then when the egg hits the pillow, then the pillow is going to act as a cushion, like it's going to dimple right there. That means the pillow prolonged the contact between the egg and the floor, literally. That's what it does. Then as a result, what happens? What would happen is like there will be like, the time will be longer. So to bring it to rest, that means you bring it to rest. That means like longer pillow, longer time, then lower force. Then lower force means then maybe the egg will survive. Another example. Boxers, they wear like their glove is like it's just like some kind of it acts as like a pillow. Why? Because like every time when there's like a punch, when one player punches the other one, the cushion normally what it does is it's going to prolong the time, because it acts as like the egg example. It acts as like the cushion is going to help to change the momentum when the player brings like that momentum, which is represented by like V mv, right? that momentum when it hits the other player, then there will be a prolonged contact between the soft material before the player really feels the real impact of the thing. That means when you increase the prolong, when you prolong or when you increase the time of contact, what would happen is the net force decreases. But if the other player didn't have the gloves, what happens is it's just like every time when you hit the other person, right? Then the contact between the player and the punch is in a very short instant of time. And then when that happens, what happens? It's a larger damage. Okay? So, you can express it like that. Or what else? I mean, in highways, in roadways, sometimes around exits, normally there is a rail guard, and if you see the rail guard, it has some kind of a spring behind it. What happens when the car comes and then hits this guy? What happens? This thing is going to bring the car into a slow contact and to stop. That means the momentum of the car, or the change in momentum of the car, the change in momentum means the impulse, right, was brought in a long period of time. It means let's say it had mass times the initial, that is its momentum, and then here its initial momentum. The final momentum is going to come to 0. If that happens in a long period of time, then the impact force between the car and the guard is going to be longer, and then then the force felt is not going to be that much. But if a car collides with a tree, there is no such a thing. This is a hard material. It hits it, right? The damage is much higher than the other one. Okay? So every time when you see something that reduces the impact, basically what it does is the impulse is not changing, but the time increased. When the time increases, the force decreases. The force experienced, the average force experienced by the colliding objects is going to get smaller. Okay, so that's what we're trying to express in terms of momentum. And so this equation that you see here is the rate of change in momentum. This is an alternative statement of Newton's second law. So in general, this change in momentum is defined as impulse I, represented by I. Okay, so the SI unit of momentum and impulse at the same time, their units is what would happen. It's going to be kilogram meter per second. Okay, because momentum is mass times velocity. All right, so the fundamental unit of mass is kilogram. The fundamental unit of velocity is meter per second. Kilogram meter per second. It doesn't have any special name. That's how you define it. Okay. So if you rearrange the equation in the previous slide, you can also find the impulse of an object, or the impulse experienced or delivered by an object is equivalent to force times delta t. Okay. All right. So this is just an extension of the previous case. All right. So you may also see how an impulse delivered in terms of force and contact time, how can it be interpreted in terms of change in momentum? You may see it for instance, you take a golf ball And then here you have the players club, right? So what would happen is like the club, right? The golf club, then it's going to come and then hit the ball. The ball initially had a momentum of 0, right? And then the club hits this, what it does is like there will be a force and there will be a contact time between the ball and the impulse. I mean, between the ball and the club. Then the golf ball starts to go, which is going to acquire a velocity. You can start with certain initial velocity, but originally it was 0, but now it gains like a final velocity. Then that is going to be PF, momentum final, and then that momentum final is M times V final. Then if you consider it like how did this object acquire a momentum? Originally it was sitting, it didn't have any kind of momentum, because if an object is not moving, then it doesn't have any momentum. So therefore, but when it's hit with the club, what is happening is the club is delivering an impulse, and the delivered impulse is translated into change in momentum by the ball. Okay, so that's how the two things are related. So that's why we are saying like impulse is equivalent to change in momentum. Okay, so here it's defined like impulse equals change in momentum. All right. Okay. So before we go ahead and then talk about like conservation of momentum and things like that, then let's try to go ahead and then like see a few more examples. Okay. Then it's a very interesting kind of concept. Momentum. It's we'll try to explain it like when we come to conservation. Then. So in your textbook, let's try. So in your textbook, let's try E1. I'm going to read it for you. E1 states like an average force is equivalent to 4,800 Newton. Acts for a time interval for how long? Force was exerted for 0.003 seconds. Question A, find, that's the required, the usual, those are given, and then you're required, or what you're asked to find is what is the impulse. Part A is asking you what is the impulse, and that's for A, and B, you're asked to find the change in momentum for this problem. Okay, so you already have the equation here. Here you have an equation. Okay, I'm just providing you. Impulse equals force times change in time, and that's the same as change in momentum. Okay, so you got 2 minutes. All right. So when we go to the solution, first we need to pick the right equation based on our given parameters. So the impulse, which is a vector quantity, is given as force times for how long, for how much time that force happened. So therefore your impulse will be equal to force, which is for 800 Newton, multiplied by 0.003 seconds. Then the amount of impulse delivered, okay, will be equal to 14.4 Newton seconds, okay. You might have said like momentum and impulse have the same unit, and this unit of momentum is kilogram meter per second. Then how come you are saying Newton second here? The two are the same, okay. So if I ask you like 1 Newton second is equivalent to 1 kilogram meter per second, the answer is yes, okay. So the two are equal. Then that's it. Then what is part B? For part B, you're asked to determine the change in momentum. But the change in momentum is the same as impulse by definition. They are the same thing. So the result, that change in momentum that you have is the same as the impulse that you just calculated. So the result is going to be 14.4 Newton second. Both have the same unit, Newton second, or you can put it like as kilogram meter per second. Alright, so that's it. Simple. More example from your textbook again. So it says number 2 or E2, it states that what is the momentum of a 1300 kilogram? So given 1300 kilogram is of course its mass. A 1300 kilogram car traveling with a speed of 27 meters per second. You're asked to determine just simply what is the momentum. So now you pick the right equation. In this case, it's going to be momentum is equal to mass times velocity based on the given parameters, right? So mass is 1300 kilogram and velocity is 27 meters per second. Multiply those two, then you get what? 31,500 kilogram meter per second. Okay. If you have used put it like in Newton second, that those two units are the same. Okay. Those two units are like the same. Let's go ahead and then add one more example and probably two more. This one is E4 or is it E3? Let's do E3. It's a comparison question. I like it. E3 states like a bowling ball has a mass, so you have bowling ball, and then you have baseball. Then it says like the baseball has a mass of 0.142 kilogram and it has a speed of 40 meters per second. Whereas the bowling ball has a mass of 7 kilograms and it has a speed equivalent to 1.5 meters per second. So the question states like, which ball had the larger momentum? larger p, let's put it that way. I'm going to give you 2 minutes. All right, so the momentum for the bowling ball, I'm going to represent it like this. For the bowling ball, it's going to be 7 kilogram multiplied by 1.5 meter per second. That will be 10.5 kilogram meter per second, right? And then momentum for the baseball will be the mass, which is 0.142 multiplied by 40. Everything is in SI unit, and the units are comparable too. Then you don't need to do any unit conversion. You just simply multiply the two values and see how much momentum you're going to get. So 5.68 kilogram meter per second. Then you look at the two values, and of course the answer is the bowling ball. Okay, so the bowling ball has a larger momentum. So, but sometimes don't be misled by the size of the object. Okay, so in this particular case, of course, it's like, the bowling ball is bigger and it has enough speed just to beat the baseball. But otherwise, like some objects, like for instance, a bullet, like it's very tiny, but at the same time it can have a tremendous amount of speed, that can have like a very large amount of momentum. Okay, so the size of the object really doesn't dictate how much momentum you have in an object. Okay, so just keep that in mind. One more probably. So E6, let's try E6. The more problems we solve, we're the better off. A ball experiences a change in momentum of, so then this the given, it says your change in momentum, literally says the change in momentum experiences 64 kilogram meter per second change in momentum. It says what is the impulse acting on the ball, right? Number one. Number two, if, so this is A, B, if the time of interaction is 0.15 second, right? Then what is the magnitude of the average force acting on the ball? So if T equals 0.15, then how much force that the ball experience? Okay, so it's like you can consider it like you hold the ball and then you bounce it on the floor or on the wall. Okay, right? So how much force does that ball experience? So it depends on for how much time it had a contact between the two balls, right? So sometimes you may say it for instance, look, I don't know, if you play let's say basketball or let's say soccer ball or that kind of thing, and then you can imagine sometimes let me put it this way, because that normally happened to me too when it's just when you play, if the ball is really well inflated. This is actually another good example that really tells you how those things are related. So if the ball is really nicely inflated, it's if it has enough air, when a player hits it, and then let's say the ball is coming, and then you do a header, or sometimes the ball can fly and then like hit you in the face, right? So this is like a well-inflated ball. You can put it as A. On the other hand, a ball isn't really quite inflated. It doesn't have enough air, that much air, and then it hits you on the face. Pretty much the two balls have the same amount of mass. Maybe they may have the same amount of speed as well. And you know, the ball isn't really inflated well when it hits you on the face. Probably, you know, it gets deformed, right? So if you take those A and B, right? So this is A is well inflated, B isn't. So which one will hurt more? A well inflated ball, which is really turgid, you know, or it's like, you know, it's a soft ball, like it doesn't have air or something like that. Yeah, definitely, it's a well inflated ball will hurt more. Why? Because there isn't much contact time. The time between, you know, my face and the ball is very small. It just slaps me and then bounces off my face. On the other hand, if the ball isn't really inflated well, it doesn't have that much air inside, like when it comes and hits me, then there will be a prolonged contact between my face and the ball. That time means, longer time means like less force, even though the impulse is the same. Okay. All right, so let's get back to our example. And so question A was what is the impulse, and question B was what is the force. All right, very good. All right, yeah, I mean, guess are awesome. So just literally, we already defined that impulse and change in momentum are the same thing. So the result, your impulse is going to be the same as what is given as change in momentum, right? On the other hand, how much force you're experiencing. So we said that like net force is equivalent to the change in momentum over time, for how long that change in momentum happened. So there is like your net force is going to be your change in momentum, which is 64 kilogram meter per second. Divide that by the time, which is 0.15 seconds, and then your net force then is going to be, what is the SI unit of force? You already know it, right? So 64 divided by 0.15, 426.67, right? So it's going to be kilogram meter per second. Per second, it means kilogram meter per second square. And that kilogram meter per second squared has a special name known as, did you say? Newton, right? Okay. Fantastic. Then now we can go to conservation of momentum. Okay. So momentum is like another phenomenon that gets conserved. Conservation of momentum. So in an isolated in an isolated system, that means like when objects collide, and then if we consider like only that collision, then in an isolated collision, then momentum is conserved. Momentum is conserved. What it means is like momentum before the objects collide is equal to, you know, the total momentum after the objects collide. Okay. Or, you know, the initial momentum of the system will eventually be conserved. I may ask you in a moment, but this every time when I feel of like the conservation of momentum, there is a question that I usually ask to my students. So the question is going to be like this. Let's assume that you are taking the conservation of momentum class. Let's say you're taking this physics class, and let's assume that let's say sometimes you see people playing on ice. Like, let's say this is just a black ice. Friction is literally zero. Okay. All right. So now, then you're at the middle of it. You're standing there. The only thing that you have, this is black ice. It's very difficult, to stand or mostly to walk, right? So you cannot walk. You can't move anywhere. The only option that you may have is maybe try to slide. But even with the sliding, it's going to be very difficult, especially there is no any friction. If there is no any kind of grip between your shoes and the ice. So this is like a very ideal kind of situation if we can create that. Then the only thing that you have in your hand is your book, your textbook, which is about 2 or 3 kilograms, let's say. Okay, even we can imagine it's 5 kilograms. So what would you do to get out of that black ice? What will you do? What will you do? So throw the book. Throw the book. So I'm going to come to that concept. But normally this is what's going to happen. If you throw the book in this direction, since there is no friction, as we said, this is an ideal scenario. What will happen is the book is going to have momentum. Okay? It's going to acquire momentum. But because of the conservation of momentum, when the book is acquiring a momentum to the right, you're going to acquire the same amount of momentum in the opposite direction. To throw the book is the right answer. Actually, it's an excellent perspective. We haven't discussed conservation of momentum yet, but yes, I'm just trying to make you think a bit. So you throw the book in that direction, then automatically you will be moving in the other direction. Since I expressed it in terms of books, of course, but you can do what if you were with your friend standing in an ice skating rink? So you're here and your friend is here. And then if you push each other, what would happen? You were standing and then eventually push hands and then let go. What would happen is your friend is going to go in this direction and you will go in this direction. That's because of conservation of momentum. That is because of conservation of momentum. Okay? So in general, momentum is conserved. There's an initial momentum and then there is a final momentum. Okay? So, one object had an initial momentum and then, for instance, you can take a cannon, right? You know, like there's a cannon like that, and then a cannonball. When the cannon shoots a cannonball, then the ball is going to go in that direction, right? And most of the time, if you see, the cannon kicks back in the opposite direction. That is also something related to conservation of momentum. Okay, we're going to come see it like in a moment. That is the recoil velocity, we call it, and that's the recoil. Okay, so that's what conservation of momentum is like. You know, one object had an initial momentum, and then like, you know, that initial momentum total has to be equal to the same as like momentum final. Just to show you diagrammatically, let's say you have two billiard balls. One is blue, the other one is some kind of beige color. And the two, they're coming and heading, and they are having head-on collision. Then the momentum of the first ball plus the momentum of the second ball before collision is equal to after collision, the sum of the momentums after the collision. Okay, so in general, mathematically speaking, this is what happens. Okay, this is the initial momentum. This is what your initial momentum looks like. That initial momentum is the same as the final momentum. Okay, initial momentum equals final momentum. All right, so momentum is conserved. Initial momentum means mass 1 had its initial momentum, mass 2 had its initial momentum. Then after they collided, mass 1 will have its initial momentum, and then mass 2 will have its final momentum. It's before and then after. Okay, so you know, we're going to do examples for when we get to types of collision, a lot more. But for now, let's go ahead and then see recoil, the concept of recoil. Concept of recoil from the perspective of conservation of momentum. Okay, so I already mentioned here, like, for instance, what happens, like, for instance, when a cannon is shot. Okay, so when you shoot a cannon, what happens? Of course, you know, then the cannon recoils. It's just, you know, this is a random kind of diagram. Okay, then there is a cannonball. Okay, so it's moving in this direction, and the cannon is going to move in this direction. How did that happen? That's because of the conservation of momentum. Originally, the cannon and the cannonball, they didn't have any kind of momentum. Their initial momentum was 0. And then at some point, when explosion happens, the cannonball is moving in, let's say, to the right. Then automatically the cannon will move to the left. Okay, so that's because of, like, you know, a concept we usually call it recoil. A gun, like, for instance, a hunting gun, is, you know, mostly like people, when they're hunting, where do they put the gun? Like, they put it on their shoulder, right? Like by their chest and their shoulder. And then every time when they shoot, what happens? Right? The gun kicks back, right? So that's what the recoil is. Okay, why the gun kicks back? Because of momentum. When the bullet leaves, so when the bullet leaves the, you know, the, what they call the barrel of the, so it's like this. So when the bullet leaves, what happens is like then the gun recoils, kicks back, and then of course you need to support it right here, mostly by the shoulder. That's why people hold it like by the shoulder, okay, because it kicks back, and sometimes that kick can be strong. Then that's what a recoil is like. So if you see here, what is happening is the following. You know, the initially, like the momentum of the shell or the bullet, you can put it like that, plus the momentum of the gun, right? So initially equals the momentum of the bullet plus the momentum of the gun. Fine. After final means after the explosion. So if you see this, initially the momentum of the bullet and the gun are zero. This is zero. Why? Because both of them were at rest inside the gun, right? So the gun is at rest and the bullet is inside the gun and it was at rest. So what you have is here now the momentum of the bullet after the explosion, of course, plus the momentum of the gun after the explosion is equivalent to zero. In other words, the momentum of the gun, if I take the gun to the other side of the equation, will be equal to the negative of the momentum of the bullet. That negative tells you like the opposite direction, nothing else. Okay, so this is an example that I'm mentioning in terms of bullet and gun example. But you remember, like in the previous question that I asked you, the momentum of U will be equal to the negative of the momentum of the book. When you throw the book, so this is an analogy that I mentioned earlier, like your U plus book, stranded in black ice. The black ice example. Okay. So you throw the book in one direction, then you will start to move in the opposite. The negative symbol just doesn't say anything. It means like opposite, in the opposite. So you two are going to have the same momentum but in opposite direction. That's what it means. And then like this, the same way is like you're standing with your friend, and at some point you guys push each other, or you push your friend with a certain momentum. If there's no friction on the floor, what would happen is like you will have your momentum and the negative is equivalent to the negative of your friend's momentum. Okay, so probably let's try to reinforce this like with examples. Then let's go ahead and then try to solve an example E12 in your textbook. I'm going to read it if you don't have it in front of you. It says like a rifle with a mass of, so the mass of the rifle is equal to 3.4 kilogram. Fires a bullet with a mass of the bullet is 7.8 gram. Keep in mind this is in gram. Then the bullet moves with a muzzle velocity. It means like when it leaves the gun is 860 meters per second. Now the question is, A, what is the momentum of the bullet after the rifle is fired? Okay. B, if there is no any external force acting on the rifle, what is the recoil velocity? V recoil. That means for the gun. Okay. I'm going to give you like probably 4-5 minutes. So simply the momentum of the bullet can be calculated as the mass of the bullet times its velocity, right? Then the momentum of the bullet will be the mass of the bullet is given as 7.8 gram. Make sure that you change that to kilogram, and it has to be inserted in terms of kilograms so that you can have the answers as SI units. Okay, so kilogram multiplied by 160. Okay, so if you simplify this, yes, you're going to get 6.07 or 70, 0.0078, multiply that by 860, 0.708 kilogram meter per second. That's it. That's for part A. So for part B, what you need to remember is the P of the bullet is equivalent to the negative of P of the rifle, right? Then P of the bullet, you already calculated it, which is 6.708, equals the negative of the mass of the rifle multiplied by P of the rifle. Okay, then I'm going to continue here. 6.708 equals the negative of the mass of the rifle is given at 3.4 kilogram multiplied by velocity of the rifle. Then to isolate, you divide both sides by negative 3.4 kilogram, then negative 3.4 kilogram. Okay, this cancels out, so therefore the velocity of the rifle will be equal to divide by that 3.4, and the answer is approximately 1.97. Everything is, yeah, you can put negative in there because we used the velocity of the bullet as positive. Just you put the negative value for the rifle's velocity just to show the rifle is kicking in the opposite direction, nothing else. Okay, so the negative just doesn't mean anything. It just means the direction of the recoil is in the opposite direction. Okay, then that's how you normally find it. Then that it's you got the answers right. So we talked about conservation of momentum, and now types of collision. So like explode, when something explodes, there is momentum conserved. Then it's a ball bouncing off a wall, momentum conserved. Two objects like collide, momentum conserved. And momentum conserved, but momentum involved. Okay, so but at the same time, yes, momentum is also conserved. Then now types of collision. There are in general like two types of collisions. One is elastic collision, the other one is inelastic collision. Okay, if the collision is inelastic, then kinetic energy is not conserved. Momentum will always be conserved in both scenarios. Okay, so if kinetic energy is not conserved, then the type of collision that you have is inelastic. Okay, inelastic. Okay, some of the kinetic energy. Why the kinetic energy? You know, whenever a collision happens, there is energy issue with that, right? There is a kinetic energy because objects are moving. So if there are kinetic energies, then some of the kinetic energy can be converted to something else. You know, when objects collide, then, you know, heat happens, a sound happens, or maybe the object is permanently deformed. You know, when two cars collide, you hear the sound, there can be heat, some of the kinetic energy will be transferred in terms of work, you know, by damaging the object and so on and so forth. So maybe, like, you know, for something that really is right in within our scope is like, maybe we may look at like a perfectly inelastic collision type. Okay, so a perfectly inelastic collision is like this. Like, for instance, you know, there is, let's say, I'm just giving an example. There's a bowling ball, you roll a bowling ball, and then there's a small baseball sitting, and then you roll the bowling ball towards the little one. Then what would happen is, mostly, like, you know, the bowling ball will stick with the small baseball, and then both of them will move together with the same common velocity. Okay, that kind of collision is known as perfectly inelastic. That means the two objects collide. After collision, they both acquire the same common velocity and they move together. You can imagine, like, a big car collides with a small car. If a small car is standing in a traffic light waiting, but if a truck from behind comes and like hits that small car, most likely both of them will go together in the direction of the bigger car. That's a perfectly inelastic collision. Okay, all right, so then that's a perfectly inelastic kind of collision. The other one is elastic head-on collision. When that happens, the momentum is conserved, the kinetic energy is conserved. You know, but most of the time, collisions aren't perfectly inelastic. They're not perfectly elastic. Sometimes, like, in between. But in general, like, just keep in mind that in an elastic collision, both momentum and kinetic energy are conserved. Okay, that's what it makes it a little different. So there is an example in your textbook. I'm going to give you like probably a few minutes to look at it. Like just a couple of minutes should be enough. And then we're going to go ahead, and then of course we're going to solve an example there. So example box 7.4. It's a perfectly inelastic kind of scenario. Okay, so if it is a perfectly inelastic scenario, what happens is, like, let me show you if there is anything about perfectly inelastic. Yeah, this is a sketch for a perfectly inelastic collision scenario. Sometimes, like, the objects may be coming together, like head-on, and then after collision, just make sure that, like, both of them have the same common velocity. Both of them have the same common velocity. Okay, so in general, like, you can find the final momentum, the final velocity, if the masses are given and if the initial momentum of the system is given. Okay, so for a perfectly inelastic collision, what usually happens is, so let's say you have mass 1, right, and you have mass 2. Okay, And then mass 1 has an initial velocity, mass 2 has an initial velocity. Okay, so this is before they collide. Initial velocity of 2. This is before. Okay. After they collide, what happens? They are going to have, like, we are going to have mass 1 and mass 2. They stick together, and then they will have a common velocity. Just simply call it v final. Right? If you see this scenario, like, then what do you have? The initial momentum of the system is equal to the final momentum of the system. What is the initial momentum of the system? Initial momentum from one, the first one, initial momentum from the second one equals, right, the final momentum of the two, both of them. But both of them are acting now after they collide as one single object, right? So if it's a common kind of question. You could be asked, like, what is the velocity after the two objects collided and experienced perfectly inelastic collision? Then, how do you proceed with that? You do the following. You have mass 1, you multiply that by the initial one, that's this, plus you have mass 2, you keep it clean, you have mass 2, the initial for object 2, equals mass 1 and mass 2 are together now, and they have v final, a common velocity. Okay. They have a common velocity. Then you'll have mass 1 v initial 1 plus mass 2 v initial 2. Divide that by the sum of the two masses. You can have this in your formula paper, for instance, to find the final velocity. Okay. If I were you, I would write this equation right on my note. Okay. So this is perfectly inelastic. Perfectly inelastic collision. Perfect inelastic collision. Okay, so I'm going to give you a couple of minutes, like just I want you to look at the example in the textbook, because that's a very good example. We're going to do a similar example, or similar problem in. So it's example says 7.4. Box 7.4. Okay. So you have 2 minutes. Just look at it. Look at how to find the problem. I mean, I can read it for you. It says 4 railroad cars, all with the same mass, 20,000 kilograms, sit on a track, as shown in the drawing. A fifth car, identical mass, approaches them with a velocity of 9 meters per second. This car collides and couples with the other 4 cars. What is the initial momentum of the system? What is the velocity of the 5 coupled cars after the collision? I can give you a diagrammatic representation. 1, 2, 3, 4. Railroad cars. And then there's a fifth one. It's moving with 9 meters per second. This is 0. You can consider this as mass 1 and the rest of them as mass 2. Okay, so this is B4. And then after what happens? You have the 4 cars, okay, and then on top of that, the 5th one came in coupled. Both of them, both of those masses will have the same common velocity. If like the mass of each is 20,000 kilograms. Okay, each car. And the very first question is, what is the initial momentum of the system, the whole system? So the collision before and after collision is considered as like one whole system. Okay, so P initial. So what's P initial? Excellent. So the initial momentum of the system, is equal to the momentum of 1 and the momentum of 2. So momentum 1 had its own mass times its own initial velocity, right? Then plus mass 1 actually, and mass of like the 4 cars, right? We're going to call it 2, I don't know, V initial 2. But V initial 2 is 0, then as a result this part will be 0. So the initial momentum is going to be mass 1, which is 20,000 kilogram, multiplied by, I'm using green, multiplied by 9 meter per second. So 180,000 kilogram meter per second. Okay. Then the other question is like, what is the velocity final after they coupled? So what we said is like after they coupled, we already put it in the above one, like is you can find it by just simply P initial divided by the mass of the two systems, right? I wrote the equation earlier, remember? Okay. So the initial momentum is 180,000 kilogram meter per second divided by mass 1 is 20,000 kilogram. Mass 2 is 4 times 20,000, which is 80,000 kilogram. You can look at the diagram that we okay, kilogram. And the kilogram cancels out. Then your V final is going to be 180,000 divided by 100,000. Right? Then that will be 1.8 meters per second. You can simplify that. So that's what the answer is. After they collided, that's what you're going to get. There is a similar problem like in the textbook, and it's E14. E14 states the following: a railroad car, now again, with a mass, so you can consider that as your mass 1, 13,000 kilogram. Collides and coupled with a second one, which is 20,000 kilogram. Now, V2 initial or V initial 2, the initial velocity of the second one, was 0. But the first one was moving 3.5 meters per second. Now the question is the same. What is the initial momentum of the first car? P initial for the first car, how much was it? And then what is the final velocity of the total, after they collided? V final. So I want every one of you to try this. Okay? So have your given parameters, copy those given parameters. Okay. Ready? Say go. Great. So P initial 1 will just be mass 1 times V initial 1, right? The first mass to 13,000 kilogram. Multiply that by 3.5 meter per second, right? So that would be 45,000, say. $45,500 kilogram meter per second. Okay. The initial momentum of the second car is 0. Okay. And already gave you how to find the final velocity in the previous. Used the green color previously. I'll just use the same. P initial 1, divide that by the sum of the two masses. Okay. If the second car had an initial velocity, right, then you would have added its initial momentum in there as well. But the initial momentum of the first car is 0, so the second car is 0, so you don't do anything there. So this will be 15, right, kilogram meter per second, and the sum of the two, that's 13,000 plus 20,000. Kilogram cancels out with kilogram, then you'll have final velocity as 45. Divide that by 33,000 meter per second. So you simplify this. Okay, so 33. Then the answer is 1.378 meter per second. Very good. Okay. Guys got it right. So pretty much we have seen everything really we're expected to see in this chapter. What's left is one topic that's that is 8.2 in your textbook. That's about torque and balance, the one that we saw just in our last lab, right? Okay. All right. So torque and balance. we tried to define torque previously, but in general, like, what is torque? Torque is it's defined as like the tendency of force to rotate something. You know, like when a force is tending to rotate an object, that's when you get a torque. Okay. Whether it's like whether it is like trying to open the cap of a water bottle, right? There's torque involved within there because you are applying force and you are tending to rotate the cap. Tending to open a door, right? How you applied, you are applying force. Okay. So in general, that's how torque is defined. It's in simple terms. It means torque is like the tendency of the force to rotate something, to rotate an object. It can be a door or a bottle cap, anything that involves like twisting and trying to open something, then that's when you have like torque. So mathematically speaking, torque in general is defined as force multiplied by the lever arm. Okay, force multiplied by the lever arm. So the lever arm, if you're applying that equation, then the lever arm and the force are perpendicular to each other. Okay, because if the force and the lever are parallel to each other, you're not going to get any torque. You're not going to get that tendency of force to rotate something. That cannot be achieved if the scenario changes. It's like, so what we're saying is like torque is equal to force times the lever arm. The lever arm represented as L, but F and L are perpendicular to each other. Okay. Yes, it makes sense, because if force and lever arm are parallel to each other, then I'm not gonna get any. So imagine like this is a door. This is where the hinge is. When you see it from the top, the door is some kind of rectangle, right? So if this is the hinge, then to open the door, so let's put two kinds of force. You have force like this, and I'm going to use another color, and then you have another force like this. You can call this force 1, and you can call this force 2. Force 2 has no torque. It doesn't rotate the door, right? It doesn't rotate the door. Why? Because when you apply the force, you're just simply squeezing along the hinge, nothing else. The force is not going to do anything. But if you look at force 1, it tends to rotate this guy along this direction, about the hinge, of course. Right? Then the distance from the hinge to where the force is, that's what your lever arm is. That's what the lever arm is. Okay, that's what the lever arm is. So you need to have the two items perpendicular to each other. Sometimes it might not be really perfectly perpendicular. Still, there has to be the part of the one that is perpendicular to the object, or the lever arm is the one that opens the door. Okay. So then in general, like you can have like multiple examples of that. As I mentioned it, like you need to twist the cap of a water bottle like this. You twist it, you're creating a torque. That's the tendency. Like you're applying the force, but it's like, if you see it from the top, if this is the top view of the cap, what you're doing is like you're applying force like this, right? There's force like this, and there's force like this. and then it's being twisted. Then there is a lever arm from the center of the cap to where you are applying the force. Alright? If you just simply push the cap in this direction, it's not going to open. You may break it, but otherwise no. Then it has to be the force has to be some kind of perpendicular to the lever arm, but otherwise it's not possible just to open it. Okay, so there's an example box in your textbook, example 8.3. It's a fully solved example. You can look at it and then you can find the problem. So the question is the following. I'm going to read it. It's partly similar to what we did in the lab. It says, suppose we have a 3 Newton weight that we want to balance against a 5 Newton weight on a beam, which is balanced when no masses are in place. The 5 Newton is placed 20 centimeters to the right of the fulcrum. Then question A, what is the torque produced by the 5 Newton? So I'm going to draw the diagram for you. So the diagram is something like this. So here is the fulcrum, and we put a 5 Newton force, and now we're trying to balance this by putting a 3 Newton force, and we're trying to balance it. So this distance is 20 centimeters. Then what should be this distance? Okay. So first of all, A, balance means balance means the torque in the clockwise must be equal to the torque in the counterclockwise. Okay. The torque in the clockwise is the same as the torque in the counterclockwise. Okay, you need to keep that in mind. So now the torque in the clockwise means this. The torque in the counterclockwise means this. The torque in the clockwise can be found as force 1 times lever arm 1. Torque in the counterclockwise means force 2 multiplied by lever arm 2. Force 1 is 5 Newton. Lever arm 1 is 20 centimeters, which is 0.2 meter. Force 2 is 3 Newton. Lever arm 2 is unknown. Then to isolate lever arm 2, you divide both sides by 3 Newton, right? Divide this by 3 Newton, you divide that by 3 Newton. The 3 Newton cancels out. Then your lever arm 2 will be 5 times 0.2 is 1 over 3 meters. So the Newton cancels out. The lever arm 2 is approximately 0.33 meter. That's equivalent to 33.3 centimeter. Okay. All right. So yeah, you may find 1 or 2 questions from the textbook that looks pretty similar to this, and you can solve them. But otherwise, there isn't much just to talk about torque. And then Of course, if you see here, like the SI unit of torque is Newton meter. Okay, just keep that in mind. Is Newton meter, and it doesn't have any special name. Remember, the SI unit of, or the fundamental unit of work done was joule, right? And that joule was the same as Newton meter. Okay, remember I mentioned like 1 joule is equal to 1 Newton meter, right? But when it comes down to torque, we don't call that as joule. Doesn't work. Just simply say it like as Newton meter. Okay, those two quantities are entirely different, even though like they may seem to have the same unit. Okay, and torque is a vector quantity, work isn't. Okay, torque is something like a twisting kind of action, and direction is important. How? If you twist something in the counterclockwise direction, it's considered as positive. If you twist something in the clockwise direction, it's expected, or the direction is meant to be negative. Okay. All right. So that's pretty much it. What I have for today. If you have any question, just let me hear it. Oh, the question that I was solving, it was an example from the textbook. It's a direct example. It's example 8-3. Okay. Yes, we have chapter 5 and 6 quiz on Thursday. We agreed for the midterm. When is it? When is the midterm? We said next Tuesday, right? Yeah. The 23rd. Tuesday or Thursday? Oh, you got me confused. I thought we said the 23rd, right? Yeah, that's Tuesday. The lecture video for chapter 5. So it is uploaded on YouTube. Okay, I'll get it. Do you have it in your answer? In the meantime, can you check it like on Blackboard Ultra? If it is recorded, you can refer it there. But otherwise, yeah. As far as I remember, I uploaded it. Maybe I didn't give you the link. Okay, but I will do so. Thank you for the reminder. Can we attempt the midterm that is under assignment for practice? No, I mean the midterm that probably you may see it on Blackboard, it's a connect one. If you then it may ask you like a connect and things like that, then it's not going to work. Okay, you'll have a hard time. But rather like there is a practice for a midterm practice. Yeah, I mean that's going to help you. Which one? The midterm practice? I thought it's there on Blackboard. Where you find the slides? Isn't it there? If you go to our course materials here, yeah, here, midterm review. No, we don't do it together, unfortunately. Yes, chapter 1 to 7 for midterm. So please do the review, sit and do it. If you have any question, you can ask me, you can send me an email. Okay. For the final, we will do a review. We'll review things together. But for midterm, okay. And most of the questions are multiple choice. Try them. Try if you can solve them. Okay. You know, it's just like similar kind of questions may show up. So. Any other question? Yeah, the midterm review is pretty much it. Yeah, set of questions for you to review them. If you see like a midterm link somewhere under assignments or somewhere, yeah, I think don't try it because it's going to be a connect kind of stuff. So yeah, there is a midterm that says under assignment, but don't try it. It was part of a connect. Okay. June, what you can do is like try them and send. You can take a picture of the like your answers and send it to me, and then I can review it, and then I can look at it, and then like, okay, this is correct, this is correct, this is not correct, kind of thing. Okay. Okay. You're welcome. You're welcome. Have a nice day. If you don't have any question, then if you want to talk to me during office hours, I'll be available. Okay. Otherwise, I'll see you tomorrow. You're welcome. See you tomorrow. You're welcome. You're welcome.